Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home on your commute or winding down for the evening, I'm really glad you're here. Now, I want you to picture this moment with me. It's December 16th, 2011. Down in Australia, there's this amateur astronomer named Terry Lovejoy, and let me tell you, the guy's about to have the night of his life. He's out in his backyard with his telescope, doing what he loves most, scanning the southern sky. Just another peaceful evening under the stars, right? Wrong. Terry spots something that, according to everything we thought we knew about space, simply shouldn't exist. He's looking at a comet, a dirty snowball from the outer reaches of our solar system, and this thing is diving straight toward the sun, not just wandering nearby, mind you. This comet is on a suicide mission, screaming toward our star at 600 kilometers per second. Now, think about that speed for a moment. 600 kilometers per second. That's fast enough to circle the entire Earth in just over a minute. This chunk of ice and rock is moving so fast that if you blinked at the wrong moment, it would travel the distance from New York to Los Angeles while your eyes were closed. But here's where it gets absolutely wild. Within days of Terry's discovery, astronomers around the world are glued to their telescopes, watching something that defies every prediction their computer models are spitting out. They're watching Comet Lovejoy because that's what they named it after its discoverer plunged directly into the solar corona. We're talking about the sun's outer atmosphere here, where temperatures hit 2 million degrees Celsius. 2 million degrees. That's hot enough to vaporize literally anything we know of in milliseconds. The comet passes just 140,000 kilometers above the sun's surface. To put that in perspective, that's about 1/3 the distance from Earth to the moon. In cosmic terms, that's practically skimming the surface. Every computer model, every physics equation, every bit of conventional wisdom says this comet should have been vaporized completely, turned into a puff of superheated gas and scattered to the solar winds. But here's the kicker, and this is the part that made scientists around the world drop their coffee cups. Comet Lovejoy emerges on the other side, intact, battered, sure. It lost a lot of mass and developed this spectacular tail that stretched millions of kilometers behind it. But the core survived. This little cosmic snowball had just performed the ultimate death-defying stunt, threading the needle through hell itself and living to tell the tale. Now I know what you're thinking. How is that even possible? Well, stick with me because this story gets even stranger, and what we learned from Lovejoy's near-death experience completely shattered everything scientists thought they knew about what happens when objects hit our star. But before we dive deeper into that cosmic collision, I want you to imagine something far more extraordinary. Picture an object from another star system entirely, not from our solar system, not from our cosmic neighborhood, but from a completely alien solar system, carrying chemistry forged in distant suns, shaped by gravitational forces we've never experienced. And this visitor is hurtling toward our own star at speeds that make Comet Lovejoy look like it's standing still. This isn't science fiction, folks. This is reality. It's already happened, and it's happening right now as we speak. You see, every single day, our sun devours countless objects. We're talking about everything from microscopic dust grains, smaller than the period at the end of this sentence, to mountain-sized comets that dwarf anything you can imagine. Most of these cosmic snacks vanish without a trace, disappearing into the sun's nuclear furnace like drops of water falling into a bonfire. But some, like our friend Lovejoy, survive to tell extraordinary tales that rewrite the textbooks. And then, in 2017, something happened that forced humanity to confront a reality that's both thrilling and slightly terrifying. The first confirmed interstellar visitor arrived. They called it Oumuamua. That's Hawaiian for first distant messenger. And boy, did it live up to its name. This wasn't just any space rock wandering through our cosmic neighborhood. This was an object from another star, carrying secrets from a solar system we'll probably never visit, moving through our space at speeds that told us immediately it didn't belong here. And just 2 years later, in 2019, another one showed up. Comet Borisov, discovered by an amateur astronomer in Crimea who was doing exactly what Terry Lovejoy had been doing, looking up at the night sky with passion and curiosity. These discoveries forced us to face something remarkable and humbling. Our sun, our seemingly stable, reliable, life-giving star, sits right in the middle of what's essentially a cosmic shooting gallery. And the bullets? They're coming from other stars. Think about that for a second. Every piece of space debris, every comet, every rogue asteroid that makes its way to our sun carries with it the story of its journey. The ones from our solar system tell us about the formation of our planetary neighborhood 4.5 billion years ago. But the interstellar visitors? They're carrying messages from alien worlds, written in the language of chemistry and physics, telling stories of star formation and planetary evolution from corners of the galaxy we may never reach. Here's what's really mind-blowing about this whole situation. For hundreds of years, astronomers assumed our solar system was pretty much isolated. Sure, we knew other stars existed, but they seemed impossibly far away. The space between stars was supposed to be empty, or at least empty enough that exchange between star systems was essentially zero. We were wrong, spectacularly wrong. The reality is that space is buzzing with interstellar traffic. Objects get kicked out of their home solar systems by gravitational interactions with giant planets, or by close encounters with other stars, or by a dozen other cosmic accidents. Once they're free, they wander the galaxy for millions or billions of years, until gravity captures them somewhere else. And our solar system? We're not just observers in this cosmic ballet. We're active participants. Every time Jupiter's massive gravity flings a comet toward the inner solar system, there's a chance it might get kicked out entirely, becoming our contribution to the interstellar community. And every so often, we receive visitors in return, cosmic ambassadors carrying chemical signatures and physical properties that tell us about the conditions around other stars. The more we've studied this process, the more incredible it becomes. Computer simulations suggest that there might be trillions of objects drifting between the stars right now. Rocks, ice balls, maybe even entire planets that got ejected from their home systems and now wander the cosmic dark. Some of them are inevitably headed our way. But here's the part that keeps me up at night, thinking about the sheer scope of what we're dealing with. Most of these interstellar objects are probably boring. I mean, scientifically fascinating, but ultimately similar to objects in our own solar system. Rock is rock, ice is ice, whether it formed around our sun or Proxima Centauri. But what if one of them isn't boring? What if the next interstellar visitor carries chemistry we've never seen before? Elements forged in stellar environments completely different from our own. What if it's made of materials that only form around certain types of stars, or in the aftermath of stellar explosions, or under gravitational conditions that don't exist in our cosmic neighborhood? The discovery of Oumuamua opened this door, and what we found on the other side challenged everything we thought we knew. This object wasn't just from another star, it was weird, really weird. It tumbled end over end every 7.5 hours, reflecting light like a mirror one moment and almost disappearing the next. Its shape defied explanation. Some scientists thought it looked like a 400-meter-long needle. Others suggested it was flat, like a cosmic pancake. And then came the real shocker. As Oumuamua left our solar system, it sped up. Not from gravity. We can calculate gravitational effects perfectly. This thing was accelerating due to some unknown force pushing it away from the sun. When comets do this, it's because they're jets of vaporizing ice acting like tiny rocket engines. But Oumuamua showed no signs of outgassing. No visible tail, no detectable jets of material. That's when things got really interesting from a scientific perspective. Yves Loeb from Harvard University made headlines around the world by suggesting that maybe, just maybe, Oumuamua might be artificial. Perhaps a light sail from an alien civilization designed to use the pressure of starlight for propulsion. Most scientists disagreed, proposing natural explanations like hydrogen ice or strange dust bunny-like structures that we'd never encountered before. But here's the thing. Nobody could prove anything, because by the time we realized how strange Oumuamua was, it was already racing beyond our reach, disappearing into the vast dark between stars. Carrying its secrets with it, the whole experience taught us something profound about our place in the cosmos. We're not isolated. We're not alone. Our sun is constantly being visited by objects from across the galaxy, each one a potential treasure trove of information about how planetary systems form and evolve around other stars. And if the thought of alien visitors isn't enough to capture your imagination, consider this. Every single one of these encounters, whether it's a comet from our own Kuiper Belt or a mysterious interstellar wanderer, represents a collision between the known and unknown. A cosmic experiment in extreme physics that we're only just beginning to understand. When these objects approach our sun, they don't just vaporize quietly. They create spectacular light shows, generate shockwaves that ripple through the solar atmosphere, and sometimes trigger magnetic storms that can affect space weather all the way out to Earth's orbit. Every impact is like ringing a cosmic bell, sending waves and disturbances propagating through our entire solar system. The sun has been playing this cosmic game of pinball for 4.5 billion years, and we've only recently learned how to keep score. Every day brings new discoveries, new understanding of just how dynamic and interconnected our cosmic neighborhood really is. So as we embark on this journey together, exploring the incredible physics of what happens when space attacks the sun, remember that we're not just talking about abstract science. We're talking about a process that's been shaping our solar system since before Earth even existed. A cosmic dance that continues right now, above our heads, every single night. And the best part, we're living through the golden age of discovery, with new telescopes coming online, spacecraft flying closer to the sun than ever before, and detection systems that can spot visitors from other stars while they're still years away. We're about to learn things about our cosmic environment that would have seemed like pure fantasy just a generation ago. But first, we need to understand how we got here. How did our sun become such a popular target? What happened during those violent early days when our solar system was still taking shape? And why does it seem like every time we think we've figured out the rules of this cosmic shooting gallery, the universe throws us a curveball that changes everything? Let's find out together. So now that you know our sun sits in this cosmic shooting gallery, let me take you back to where this whole wild story really begins. We need to travel way, way back in time, 4.5 billion years ago to be exact. Picture this. Our sun isn't the stable, mature star we know today. It's a cosmic toddler barely formed, and let me tell you, it's making one heck of a mess. In the beginning, chaos absolutely reigned. Our infant sun was surrounded by what astronomers call a protoplanetary disk, basically 100 Earth masses worth of leftover building materials from stellar formation. We're talking about rock, ice, and dust, all swirling around in this incredible gravitational maelstrom. Imagine the most chaotic construction site you've ever seen, then multiply that by about 1 trillion and set it in space. That's what our early solar system looked like. Here's what's wild about young stars. They're incredibly messy eaters. And our sun was no exception to this rule. Picture a cosmic buffet where everything is flying around at thousands of kilometers per hour, and you've got this hungry young star in the middle, gravitationally grabbing everything it can reach. Every few minutes, and I mean every few minutes, another chunk the size of Mount Everest would spiral into the sun's gravity well and just vanish in a brilliant flash of vaporized rock and ice. Think about that for a second. Every few minutes, something the size of the world's tallest mountain would disappear in a burst of energy that would make our most powerful nuclear weapons look like firecrackers. The early solar system was like the ultimate cosmic demolition derby, with collisions so frequent and so energetic that the sun's surface literally couldn't cool down between impacts. The energy being released was absolutely staggering. Each impact delivered more energy than all of human civilization has used in our entire history, and this was happening continuously for millions of years. The sun was basically being carpet-bombed by mountain-sized projectiles, and the bombardment was so intense that our star was actually brighter and more active than it is today, despite being younger and smaller. But here's where it gets really interesting. This wasn't just random destruction, it was construction in disguise. All of this cosmic violence was actually the process of our solar system organizing itself. Jupiter was forming out there in the cold outer regions, growing massive enough to start bullying smaller objects around with its gravity. Saturn was doing the same thing. These giant planets were like cosmic vacuum cleaners, sweeping up material and fundamentally reshaping the architecture of our entire solar system. And then something remarkable happened. Jupiter started migrating inward. Computer simulations show that our giant planet actually moved much closer to the Sun than it is today, then mysteriously migrated back outward. This cosmic shuffle had profound consequences for everything else in the solar system. As Jupiter moved around, its massive gravity field acted like a cosmic slingshot, flinging ice-rich comets from the outer solar system toward the inner planets. This is where the story gets personal for us here on Earth. Those Jupiter-flung comets weren't just cosmic debris, they were water delivery systems. During what scientists call the Late Heavy Bombardment, about 4 billion years ago, our young planet was getting pummeled by these icy visitors from the outer solar system. Each impact delivered not just energy, but precious water and organic compounds. In a very real sense, the cosmic chaos that was devastating the early solar system was also seeding Earth with the ingredients for life. Fast forward through the eons, past the formation of the planets, past the cooling of Earth's surface, past the emergence of life itself. Jump ahead to just 2,000 years ago, when Chinese astronomers were doing something absolutely remarkable without even realizing it. They were meticulously recording what they called broom stars, comets that swept close to the sun with their distinctive tails trailing behind them like cosmic broomsticks. These ancient astronomers had no idea they were documenting solar system archaeology in action. Every comet they recorded was a time capsule from the formation of our solar system, a dirty snowball that had been orbiting in the cold outer reaches for billions of years before finally taking a dive toward our star. They were watching the ongoing cleanup process, the final act of solar system formation playing out in slow motion across the centuries. Some of these ancient encounters were absolutely spectacular. The Great Comet of 1843 came so close to the sun that observers could see it in broad daylight. Imagine looking up at the afternoon sky and seeing a comet so bright it outshone everything except the sun itself. Its tail stretched halfway across the sky, a ghostly banner visible even through the glare of daylight. People were terrified, thinking it was an omen of the end times. They had no idea they were witnessing one of the most extreme close encounters between a comet and our star in recorded history. But the real revolution in understanding solar impacts came with the space age. Suddenly, we had eyes in space, telescopes and cameras that could watch the sun continuously without worrying about clouds or daylight or atmospheric interference. And what we discovered completely transformed our understanding of how active and dynamic the space around our sun really is. On August 31st, 1979, a spacecraft called Solwind captured something extraordinary. Howard Russell, analyzing the data, spotted what appeared to be a comet plunging directly into the sun and completely disintegrating. This wasn't just another close approach. This was total annihilation, caught on camera for the first time in human history. Howard had just discovered the first sungrazer caught in the act of cosmic suicide. You're not going to believe how this discovery happened. Russell was actually looking for something completely different. He was studying the solar corona, trying to understand the sun's outer atmosphere, when he noticed this bright streak moving across his images. At first, He thought it might be an instrument malfunction or maybe a piece of space debris. But as he tracked the object across multiple images, he realized he was watching something unprecedented, a comet dying in real time, vaporizing completely as it dove into the solar furnace. This discovery opened floodgates. Once we knew what to look for, we started finding suicidal comets everywhere. The Solar and Heliospheric Observatory, launched in 1995, revolutionized the field. SOHO, as it's known, sits at a gravitationally stable point between Earth and the Sun, watching our star continuously with multiple instruments. And what it's shown us is mind-blowing. SOHO has discovered over 4,000 comets diving into the Sun. 4,000. That's more comet discoveries than all of ground-based astronomy combined throughout human history. We're talking about cosmic kamikaze missions happening almost daily. A constant parade of dirty snowballs meeting their doom in the solar furnace. But here's what's really wild. Most of these comets belong to what's called the Kreutz family. They're all fragments of one massive comet that broke apart centuries ago, probably sometime around the 12th century. This parent comet must have been absolutely enormous, maybe tens of kilometers across. When it shattered, it created thousands of smaller pieces, all following similar orbits that bring them screaming back toward the Sun at regular intervals. Think about this cosmic family reunion happening in slow motion. For 800 years, these fragments have been returning to the scene of their parents' destruction, diving one by one into the Sun in a spectacular light show that continues to this day. It's like watching the universe's longest, slowest fireworks display, with each explosion separated by months or years. Today, we know the Sun encounters material constantly. The Parker Solar Probe, launched in 2018, has revolutionized our understanding by actually flying through the solar corona itself. This incredible spacecraft gets closer to the Sun than any human-made object in history, and what it's discovered is that space near our star is far from empty. Parker has shown us that there's a constant rain of particles falling into the Sun, dust grains so small you could fit millions of them on the head of a pin, creating the zodiacal light, that faint glow you can sometimes see in the sky just after sunset or before sunrise. These microscopic impacts might seem insignificant, but collectively they represent tons of material hitting the Sun every single day. And then there are the big ones, the massive Kreutz comets that put on spectacular shows as they make their final approach. Parker has flown through the aftermath of these cosmic collisions, measuring magnetic field disturbances and shock waves that propagate outward through the solar wind. The spacecraft has essentially become our eyes and ears in hell, sending back data from the most extreme environment in our solar system. The technology for discovering these solar impacts has become absolutely incredible. Software like the Sungrazer project enables amateur astronomers worldwide to search through spacecraft images and spot doomed comets in their final hours. You can literally sit at your computer, download images from space-based solar observatories, and discover a comet that no human has ever seen before. Just hours before it vaporizes in the solar corona, this citizen science approach has been phenomenally successful. Amateur astronomers have discovered hundreds of sun-grazing comets, contributing to our understanding of these cosmic death spirals from their living rooms and backyard observatories. It's democratized the process of discovery in a way that would have been unimaginable just a few decades ago. Every year brings about 3,000 new comet discoveries, and a significant fraction of these are objects on collision courses with the Sun. We're essentially watching solar system archaeology in real time, as these ancient remnants from the formation of our cosmic neighborhood finally complete their billion-year journeys back to their birthplace. But here's what really gets me excited about all this. The Sun has been playing this cosmic game of pachinko for 4.5 billion years, and we're just now learning to keep score. Every impact, every vaporization, every spectacular disintegration is teaching us something new about the physics of our star. the chemistry of comets, and the dynamic evolution of our solar system. The bombardment continues today, right now as we speak. Somewhere in the outer solar system, there are comets beginning their final inward spiral. In the asteroid belt, gravitational perturbations are slowly nudging rocky objects onto Earth-crossing orbits that might eventually bring them close enough to the Sun for a spectacular finale. And from the depths of interstellar space, visitors from other star systems are racing toward our cosmic neighborhood, carrying chemical signatures and physical properties that will teach us about planetary formation around distant suns. This isn't ancient history we're talking about. This is an ongoing process, a cosmic conversation between our sun and the universe at large that's been continuing for billions of years and shows no signs of stopping. Every clear night, telescopes around the world and spacecraft throughout the solar system are watching, waiting, recording the next chapter in this incredible story of cosmic collisions. And just when we thought we had the whole process figured out, the universe threw us a curveball that changed everything. Because in 2017, we detected something that shouldn't have been possible. Visitors from another star system entirely, carrying secrets from alien suns and challenging everything we thought we knew about our place in the cosmic neighborhood. That's when this whole story got really interesting. October 19th. 2017 started like any other night at the Haleakala Observatory in Hawaii. Robert Verick was doing what astronomers do best, methodically reviewing images from the Pan-STARRS telescope, looking for anything unusual in the vast catalogue of space objects that cross our sky every night. It's painstaking work, the kind of careful attention to detail that most people would find mind-numbingly boring. But for astronomers like Robert, it's treasure hunting on a cosmic scale. Then he noticed something odd. In the middle of all the familiar star patterns and known asteroids, there was this faint dot moving too fast to be anything normal. Way too fast. Robert had been doing this for years, and he'd never seen anything quite like it. Within hours, he'd alerted observatories around the world, and suddenly astronomers everywhere were dropping whatever they were, doing to point their telescopes at this mysterious visitor. What they found changed everything we thought we knew about our place in the galaxy. They named it Oumuamua. That's Hawaiian for first distant messenger, and boy, did it live up to its name in ways nobody could have predicted. This wasn't just another asteroid or comet from the outer reaches of our solar system. The math was absolutely clear. This object was moving too fast and in the wrong direction to have originated anywhere in our cosmic neighborhood. It was an interstellar visitor, the first confirmed object from another star system that humanity had ever detected. Think about what that means for a moment. For all of human history, everything we'd ever studied in space, every planet, every asteroid, every comet, every speck of dust, had been part of our solar family. Sure, we knew other star systems existed, but they were so impossibly far away that the idea of actually receiving visitors from them seemed like pure science fiction. And yet here was Oumuamua, racing through our solar system, carrying secrets from a place we'd never imagined we could study up close. But Oumuamua wasn't just visiting from another star. It was absolutely mind-bendingly weird. And I mean weird in ways that challenged our fundamental understanding of what space objects should look like and how they should behave. First, there was the tumbling. Oumuamua was spinning end over end every 7.3 hours, but it wasn't just rotating like a normal asteroid. The way it reflected sunlight as it tumbled told us something incredible about its shape. One moment it would be relatively bright, reflecting light like a cosmic mirror. Then as it continued its rotation, it would become dramatically dimmer, almost disappearing from our telescopes. Entirely, this dramatic change in brightness meant that Oumuamua was either incredibly elongated, like a cosmic needle stretching 400 meters long, but only about 40 meters wide, or it was flat like a cosmic pancake, perhaps only a few meters thick but hundreds of meters across. Either way, it was unlike anything we'd ever seen before. Asteroids in our solar system are generally roughly spherical, maybe a bit lumpy, but nothing like the extreme proportions that Oumuamua seemed to have. But the real shock came when astronomers started tracking its path more precisely. As Oumuamua raced away from the sun and headed back toward interstellar space, something impossible happened. It sped up. Not by much. We're talking about tiny changes in velocity that required incredibly precise measurements to detect. But the acceleration was definitely there, and it was definitely real. Now here's why this was so shocking. We can calculate gravitational effects with incredible precision. We know exactly how fast an object should be moving at any given distance from the sun based purely on gravity. But Oumuamua was moving faster than gravity alone could account for. Something was giving it an extra push. When comets accelerate as they approach the sun, we know exactly what's happening. The sun's heat vaporizes ice on the comet's surface, creating jets of gas and dust that act like tiny rocket engines. We can see these jets with our telescopes, and we can detect the gas and dust they produce with our instruments. It's a well-understood process that we've observed thousands of times, but Oumuamua showed no signs of outgassing. No jets of material, no visible tail, no detectable traces of gas or dust. By every measure we had, this object appeared to be a bare rock, yet it was accelerating like a comet. It was as if someone had given it an invisible engine that we couldn't detect with any of our instruments. That's when Avi Loeb from Harvard University made headlines around the world. In a paper that sent shockwaves through the scientific community, Loeb suggested that maybe, just maybe, Oumuamua might be artificial. Perhaps it was a light sail from an alien civilization, designed to use the pressure of starlight itself for propulsion. Now, I want to be clear here, this was an extraordinary claim. And as Carl Sagan famously said, extraordinary claims require extraordinary evidence. The vast majority of scientists disagreed with Loeb's interpretation. They proposed alternative natural explanations that were admittedly exotic, but didn't require invoking alien technology. Some suggested that Oumuamua might be made of hydrogen ice, a material so exotic that it doesn't exist naturally anywhere in our solar system, but might form in the incredibly cold environment between stars. As this hydrogen ice sublimated in the warmth near our sun, it might not produce visible jets, but could still create enough thrust to explain the mysterious acceleration. Others proposed that Oumuamua might have a strange, dust bunny-like structure with an incredibly low density, making it more susceptible to radiation pressure from sunlight. Or maybe it was made of materials we'd never encountered before, with properties that allowed solar radiation to push it around in ways we hadn't predicted. But here's the frustrating part. By the time we realized just how strange Oumuamua was, it was already racing beyond our reach. We had maybe a few weeks to study it before it disappeared forever into the vast darkness between stars, carrying all its secrets with it. Every telescope on Earth and in space was pointed at this cosmic messenger. But we were essentially trying to solve a murder mystery, while the only witness was driving away at 60,000 kilometers per hour. The whole experience was both thrilling and heartbreaking. Here was humanity's first confirmed visitor from another star system, and we were completely unprepared for it. We didn't have spacecraft ready to intercept it. We didn't have the right instruments to analyze its composition. And we certainly weren't expecting it to behave in ways that challenged our basic understanding of physics. But Oumuamua taught us something profound. It showed us that the galaxy is far more connected than we'd ever imagined, and that our solar system regularly receives visitors carrying information from corners of the universe we thought were permanently beyond our reach. Then, just 2 years later, the universe decided to give us another chance. In August 2019, amateur astronomer Gennady Borisov was doing exactly what Terry Lovejoy and countless other sky watchers do, scanning the heavens with his homemade telescope from his observatory in Crimea. Gennady had built this telescope himself, a labor of love driven by pure curiosity about what might be lurking in the cosmic dark. And on this particular night, his dedication paid off in spectacular fashion. He spotted what would become humanity's second confirmed interstellar visitor. They named it Comet Borisov, after its discoverer, and it was everything that Oumuamua wasn't. Where Oumuamua had been mysterious and alien, Borisov was remarkably familiar. Comet Borisov was clearly a comet, complete with the classic signs we'd expect: a bright nucleus surrounded by a fuzzy atmosphere of gas and dust, and a beautiful tail streaming behind it as it approached the sun. It looked almost exactly like comets from our own solar system, except for one crucial detail. Its speed and trajectory made it absolutely clear that this visitor had come from another star. This raised even more questions than it answered. If interstellar comets look just like our comets, what does that tell us about planet formation across the galaxy? Are the physical and chemical processes that created our solar system universal? Do all planetary systems go through similar evolutionary stages? Scientists around the world scrambled to study Borisov before it completed its brief visit and disappeared back into interstellar space. They detected water vapor streaming from its nucleus, carbon monoxide gas, and other familiar molecules. The chemical signature was remarkably similar to comets in our own solar system, suggesting that the basic building blocks of planetary systems might be the same throughout our local region of the galaxy. But there were subtle differences too. The ratio of carbon monoxide to water was higher than in most comets from our solar system, hinting at formation conditions that were just slightly different from what we see in our cosmic neighborhood. It was like comparing two recipes for the same dish, recognizably similar, but with just enough variation to tell you they came from different kitchens. The discovery of Comet Borisov also confirmed something that astronomers had suspected but couldn't prove. Interstellar visitors are probably much more common than we'd realized. If we could detect two of them within just a few years of seriously looking, that suggested there might be hundreds or thousands of these cosmic wanderers passing through our solar system every year, most of them too small or too faint for us to spot with current technology. Computer simulations started painting a picture of a galaxy absolutely buzzing with interstellar traffic. Every time a giant planet gravitationally kicks an object out of its home solar system, that object becomes a cosmic nomad, wandering the galaxy until it's captured by another star or collides with something. The process has been going on for billions of years, creating a vast cloud of interstellar debris that permeates our entire region of the galaxy. This means that right now, as we speak, there are probably dozens of interstellar objects passing through our solar system. Most are too small to detect, moving too fast to study, or following trajectories that don't bring them close enough to Earth for our telescopes to spot them. But they're out there, invisible messengers from alien suns, carrying chemical fingerprints and physical properties that could teach us incredible things about how planetary systems form and evolve. The implications are staggering. Every interstellar visitor is essentially a free sample from another solar system delivered right to our cosmic doorstep. We don't have to travel to other stars to study alien worlds. The alien worlds are coming to us, one visitor at a time. But perhaps the most profound realization is this: the discovery of Oumuamua and Comet Borisov has forced us to acknowledge that our solar system isn't the isolated island we once thought it was. We're part of a vast galactic ecosystem, constantly exchanging material with other star systems through a process that's been going on since the galaxy was young. Think about what this means for the distribution of life in the universe. If rocky and icy objects can travel between star systems, carrying organic molecules and perhaps even microorganisms, then the galaxy might be far more biologically connected than we've ever imagined. The process is called lithopanspermia, the idea that life could spread from world to world through natural processes, hitching rides on asteroids and comets that get kicked out of their home systems and captured elsewhere. It's entirely possible that the organic molecules essential for life on Earth originally came from another star system, delivered by ancient interstellar visitors that arrived billions of years ago when our planet was still cooling. And if that's true, then life itself might be a galactic phenomenon, spreading from star to star through the slow but persistent process of interstellar exchange. The discovery of these interstellar visitors has also revolutionized our thinking about planetary defense. We've spent decades cataloging asteroids and comets in our solar system that might pose a threat to Earth, but now we realize we also need to watch for visitors from other stars. These objects approach from random directions at incredible speeds, giving us very little warning time compared to objects that have been orbiting our sun for billions of years. But perhaps most importantly, Oumuamua and Comet Borisov have shown us that we're living in the early days of a new era of astronomy. We're transitioning from studying our own solar system to studying samples from across the galaxy, delivered free of charge by the universe itself. Every interstellar visitor is a time capsule from another world, carrying information about stellar evolution, planetary formation, and perhaps even biological processes from corners of the galaxy we may never visit in person. The message is clear. Our solar system sits at the intersection of countless cosmic highways, with traffic flowing in from every direction. We're not alone in the cosmic dark. We're part of a vast, interconnected galactic community. And the visitors are arriving whether we're ready for them or not. And here's the really exciting part. We're just getting started. New telescopes coming online in the next few years will be able to detect interstellar visitors while they're still years away from their closest approach to the sun. We'll have time to plan missions, design instruments, and maybe even intercept these cosmic messengers to study them up close. The age of interstellar archaeology has begun, and we're the first generation of humans to participate in it. Every new visitor teaches us something about our place in the galaxy, and every discovery brings us closer to understanding the cosmic processes that shape planetary systems throughout the universe. But now we need to dive deeper into what actually happens when these visitors reach their destination. Whether they're from our own solar system or from distant stars, whether they're mountain-sized comets or microscopic dust grains, they all face the same ultimate test when they encounter our sun. Let's take a journey into the solar furnace itself and see what happens when space truly attacks our star. All right, now we're going to take a journey that no human will ever experience firsthand. But thanks to our spacecraft and computer simulations, we can understand in incredible detail. We're going to follow an object, let's say a comet from the outer solar system, on its final death spiral into our sun. This is a journey from the cold, dark reaches of space into the most extreme environment in our solar system. And what happens along the way is absolutely mind-blowing. So here's what actually happens in those final moments when an object meets our star, step by terrifying step. Let's start our doomed visitor's journey 20 million kilometers from the sun. To put that in perspective, that's about half the distance from the sun to Mercury when Mercury is at its closest approach. At this distance, our comet is already beginning to feel the sun's true power in ways it never has before during its billion-year slumber. In the outer solar system, solar radiation pressure. And this is one of those physics concepts that sounds simple, but is actually mind-bending. When you think about it, starts becoming a real factor. Light has momentum. Photons, the particles of light streaming away from the sun, actually push on objects they hit. For most situations, this pressure is incredibly tiny. But when you're dealing with an object that's been carved and shaped by eons of cosmic weathering, every bit of pressure matters. At 20 million kilometers, something remarkable starts happening. The solar radiation pressure begins competing with gravity itself. Think about that for a second. The push of pure sunlight is actually strong enough to fight against the gravitational pull of an object with the mass of our sun. For small particles and dust grains, radiation pressure can completely overcome gravity. blowing them away from the sun like cosmic dandelion seeds in a stellar wind. But our comet is much more massive, so gravity still wins this tug of war. The radiation pressure does something more subtle, but equally important. It starts acting like a brake, slightly slowing the comet's rotation and beginning the process of stripping away the finest particles from its surface. These microscopic grains form the very beginning of what will eventually become a spectacular tail. Now let's move closer. By 10 million kilometers from the sun, the temperature surrounding our visitor passes 1,000 degrees Celsius. This is where things start getting really dramatic, really fast. Any water ice on the comet's surface begins sublimating violently, going directly from solid ice to water vapor without bothering with the liquid phase. This isn't the gentle sublimation you might see from dry ice on a laboratory bench. This is explosive outgassing that can create jets powerful enough to spin the entire comet like a cosmic Catherine wheel. The SOHO spacecraft has captured this process thousands of times, and it's absolutely spectacular to watch. Comets that have been invisible specks suddenly brighten dramatically as they cross this threshold of destruction. The sublimating ice doesn't just disappear. It creates jets of gas and dust that can extend for hundreds of thousands of kilometers behind the comet, forming the classic tail that makes these objects so beautiful and terrifying. But here's where the physics gets really interesting. The jets aren't symmetrical. They don't just stream straight back from the sun. The comet's rotation means these jets are like cosmic sprinklers, creating spiral patterns of gas and dust that can actually change the comet's orbit through a process called the Yarkovsky effect. The comet is essentially creating its own tiny rocket engines, and the thrust from these jets can speed it up, slow it down, or even nudge it onto a slightly different trajectory. Let's continue our journey inward. At 5 million kilometers from the sun, we encounter one of the most fascinating and destructive forces in the solar system. This is where the sun's gravity starts winning a completely different kind of tug-of-war, not with radiation pressure, but with the comet's own structural integrity. Imagine stretching taffy, but the taffy is made of rock and ice, and the force pulling it apart increases exponentially as you get closer to the source. This is the Roche limit in action, the point where tidal forces overcome the object's self-gravity. For a typical comet, this catastrophic threshold occurs at about 2.4 solar radii from the sun's center. The physics here is both elegant and terrifying. The side of the comet facing the sun experiences stronger gravitational pull than the side facing away. This difference in gravitational force, the tidal force, tries to stretch the comet like cosmic silly putty. At first, the comet's internal structure can resist this stretching. But as it gets closer to the sun, the tidal forces become overwhelming. The comet begins to elongate, first imperceptibly, then dramatically. Cracks propagate through its structure at the speed of sound in ice, about 2 kilometers per second. If you could somehow be there to watch, you'd see the object literally pulling itself apart, with chunks breaking off and following slightly different orbits that spread them out in a line behind the main body. This process has been captured in stunning detail by space-based telescopes. We've watched comets break into dozens of fragments, each piece following its own path towards solar destruction. The most famous example was Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces and then slammed into the giant planet in 21 separate impacts. When similar breakups happen near the sun, the result is even more spectacular because each fragment becomes its own individual firework in the solar furnace. Now, we're really entering hell itself. By the time our doomed visitor reaches the solar corona at about 2 million kilometers altitude above the sun's visible surface, it's entering an environment so extreme that it challenges our basic understanding of matter and energy. The corona's temperature jumps to 2 million degrees Celsius. 2 million degrees! That's more than 100 times hotter than the sun's visible surface, a paradox that scientists are still working to fully understand. But here's the weird thing about temperature in the near vacuum of space. It works differently than temperature in air. The particles in the corona are incredibly hot, but there aren't very many of them. It's like the difference between getting hit by a few very fast-moving baseballs versus being caught in a rainstorm. The individual particles have enormous energy, but the overall density is so low that the heating effect is more gradual than you might expect. The real killer isn't the hot gas, it's the radiation. Our comet is suddenly bathed in X-rays and extreme ultraviolet light that can penetrate meters deep into its structure. This isn't gentle heating from the outside in. This is explosive vaporization from the inside out, as high-energy photons deposit their energy deep within the comet's interior and create expanding bubbles of superheated gas. But wait, there's more. At the speeds we're talking about, 600 kilometers per second for a typical sun-grazing comet, even the thin plasma of the solar corona hits like a sledgehammer. This is called ram pressure, and it's the cosmic equivalent of trying to swim through concrete. For an object traveling at these incredible speeds, the pressure from hitting even the sparse coronal material equals millions of atmospheres. Think about what that means. The comet is simultaneously being cooked by radiation, stretched apart by tidal forces, explosively outgassing from internal heating, and smashed by ram pressure from material it's plowing through. It's facing every form of destruction the universe has to offer, all at the same time. The combination of all these forces creates something that can only be described as a cosmic catastrophe in fast motion. The object doesn't just melt. It explodes in a chain reaction of vaporization that can release as much energy as 1 million nuclear bombs. The Parker Solar Probe has actually flown through the aftermath of these explosions, detecting magnetic field disturbances and shock, waves that propagate outward through the solar wind past Earth's orbit. Let me paint you a picture of what this looks like from our spacecraft watching safely from millions of kilometers away. The comet brightens suddenly and dramatically as it enters the corona, sometimes becoming visible to telescopes even in broad daylight. Its nucleus, the solid core that's been preserved for billions of years in the cold outer solar system, begins to disintegrate in real-time. Material streams away from the dying comet at hundreds of kilometers per second, creating a glowing cloud of ionized gas that can extend for millions of kilometers. The magnetic field embedded in the solar wind gets twisted and distorted by all this newly created plasma, creating waves and disturbances that race outward at nearly the speed of light. But here's what's absolutely fascinating from a scientific perspective. This isn't just destruction for destruction's sake. These cosmic explosions are incredible natural experiments in extreme physics. The temperatures and pressures created during a comet's final moments exceed anything we can produce in our most advanced laboratories. We're watching matter behave under conditions that exist nowhere else in our solar system except in the sun's core itself. The Parker Solar Probe has revolutionized our understanding of these processes by actually flying through the scene of the crime. This incredible spacecraft gets closer to the sun than any human-made object in history, and what it's discovered about the corona has completely rewritten our textbooks. The probe has shown us that the space near the sun is incredibly dynamic and structured. There are magnetic field lines that channel the solar wind into streams and jets. There are acoustic waves bouncing through the corona like cosmic thunder. And there are the remnants of countless comet impacts, magnetic disturbances, and particle clouds that tell the story of objects that met their doom years or even decades earlier. One of Parker's most surprising discoveries is that the corona is full of what scientists call switchbacks, sudden reversals, in the magnetic field that create S-shaped curves in the solar wind. Many of these switchbacks might be created by the explosive vaporization of small comets and asteroids, each impact sending shockwaves through the corona that persist long after. The original object has completely disintegrated. The probe has also detected something called dust devils in the corona, concentrated streams of particles that spiral through the magnetic field lines like cosmic tornadoes. These might be the ghosts of comets past, material that was blasted off during impacts and is still circling the sun in complex magnetic loops. But perhaps the most mind-blowing thing Parker has shown us is just how much material is constantly falling into the sun. We're not just talking about the spectacular comets that make headlines. There's a constant rain of smaller objects, chunks of asteroids, pieces of ancient comet breakups, microscopic dust grains, and probably fragments of interstellar visitors we'll never detect individually. The probe has measured this cosmic precipitation directly, flying through clouds of particles and detecting the tiny impacts as they hit its heat shield. It's like standing in a gentle rain, except each raindrop is moving at hundreds of kilometers per second and is hot, enough to vaporize instantly on contact. What's really remarkable is that the sun seems to be remarkably efficient at processing all this incoming material. Very little of it actually makes it to the sun's surface. Most objects are completely vaporized in the corona, their energy absorbed by the solar atmosphere and contributing to the complex dynamics that drive space weather throughout the solar system. The magnetic field plays a crucial role in this process. The sun's magnetic field lines act like cosmic highways, channeling the debris from impact sites and distributing the energy throughout the corona. Sometimes this creates spectacular magnetic reconnection events, cosmic short circuits that can release as much energy as billions of nuclear bombs and send shock waves racing through the entire solar system. But here's where it gets really interesting from an astronomical perspective. Each impact is unique, like a cosmic fingerprint that tells us about the object that created it. The spectral lines in the light emitted during vaporization reveal the chemical composition of the original comet or asteroid. We can literally read the periodic table in the light of these cosmic explosions. Rocky asteroids create different spectral signatures than icy comets. Objects from the outer solar system have different chemical fingerprints than objects from the asteroid belt. And interstellar visitors, well, they might carry chemical signatures we've never seen before, forged in stellar environments completely different from our own. The energy signatures are distinctive too. Small dust grains create brief flashes that last milliseconds. Mountain-sized comets create explosions that can be detected for hours or even days. And the hypothetical really massive objects, rogue asteroids or fragments of shattered moons, would create disturbances so large they might affect the sun's entire atmosphere for weeks. All of this is happening right now above our heads, every single day. While we go about our daily lives, the sun is being bombarded by a constant stream of cosmic debris, each impact a miniature supernova that releases energies beyond human comprehension. The Parker Solar Probe and other spacecraft are our eyes and ears in this cosmic battlefield, sending back data that's helping us understand not just our own star, but the fundamental physics that governs the universe itself. The really wild part is that this process has been going on for 4.5 billion years, and it's going to continue for billions more. The sun has been playing this cosmic game of target practice since before Earth even existed, and it's become incredibly good at it. But what happens when something really different comes along? What if the next visitor isn't just another icy comet or rocky asteroid? What if it's something so unusual, so extreme, that it challenges everything we think we know about how these cosmic collisions work? That's exactly what we need to explore next. Now let's push the boundaries of cosmic possibility into territory that's going to make you look at our sun in a completely different way. Everything we've discussed so far assumes what scientists call normal objects, ice and rock, moving at typical interstellar speeds, following predictable physics as they meet their doom in the solar furnace. But here's the thing about the universe. It rarely limits itself to normal. The cosmos has had 14 billion years to create oddities beyond our wildest imagination. and statistically speaking, some of them are inevitably headed our way. So let's explore what happens when the next interstellar visitor is fundamentally different from anything we've encountered before. Start with speed. When Oumuamua entered our solar system, it was moving at 26 kilometers per second relative to the Sun. That sounds incredibly fast. And it is by human standards, but in cosmic terms, it's actually quite leisurely. But rogue objects ejected from binary star systems, or materials flung out by supernovas, or debris accelerated by encounters with massive black holes, can reach velocities that make Oumuamua look like it's standing still. Imagine an object traveling at 1,000 kilometers per second. That's about 40 times faster than Oumuamua, and objects moving at these speeds have actually been detected in the galaxy. At 1,000 kilometers per second, a visitor would cross our entire solar system in just 6 weeks, giving us almost no time to study it before it vanished back into interstellar space. But the physics changes dramatically at these extreme velocities. The kinetic energy of a moving object increases with the square of its velocity, which means that small increases in speed translate to enormous increases in destructive potential. An object moving at 1,000 kilometers per second carries 40 times the speed, but 1,600 times the kinetic energy of the same object at typical interstellar velocities. Now let's really push the envelope. What if we encountered an object moving at 1% the speed of light? That's 3,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in less than 2 minutes. Objects moving at these relativistic speeds have been observed being ejected from the vicinity of supermassive black holes, accelerated by magnetic field interactions that can channel enormous amounts of energy into relatively small chunks of matter. At 1% the speed of light, the physics becomes truly exotic. A 1-kilometer metallic object at this velocity would carry kinetic energy approaching 10 to the 27th joules. To put that in perspective, that's roughly equivalent to the energy released by a stellar explosion concentrated into a single impacting body. When this cosmic bullet hits our sun, it wouldn't just vaporize. It would deliver enough energy to power human civilization for 1,000,000 years, all released in microseconds. Computer simulations of such an impact are absolutely mind-bending. The object would penetrate deep into the sun's interior before its kinetic energy was fully absorbed, creating a shock wave that would race through our star at 500 kilometers per second. The sun would literally ring like a cosmic bell, with acoustic waves bouncing through its interior for weeks or even months. But here's where it gets really terrifying from our perspective here on Earth. The impact would trigger a massive solar flare unlike anything in recorded history. The sudden injection of energy would accelerate particles in the sun's magnetic field to near light speed, creating a blast of radiation that would reach Earth in just 8 minutes. Our planet's magnetic field and atmosphere would protect us from the worst effects, but satellites would be fried, power grids could fail, and the aurora would be visible from the equator. The long-term effects might be even more dramatic. Solar physicists have run simulations suggesting that such an impact could trigger changes in the sun's internal structure that would persist for years. Our star might become more active, producing more frequent and more powerful solar flares. Or conversely, the shock might disrupt the internal processes that drive solar activity, potentially triggering a period of reduced solar output, similar to the Maunder minimum that contributed to the Little Ice Age in the 17th century. But what if mass, rather than speed, makes the difference? In 2022, astronomers using gravitational lensing techniques made a startling discovery: rogue planets. We're talking about world-sized objects drifting between the stars without a sun to call home. Current estimates suggest there might be trillions of these cosmic nomads wandering our galaxy, invisible orphans ejected from their birth systems by gravitational interactions with giant planets or close encounters with other stars. Most rogue planets are probably similar in size to Earth or smaller, but some could be as massive as Jupiter or even larger. Now imagine what would happen if a rogue planet the mass of Mercury, about 5% of Earth's mass, encountered our Sun. The destruction would unfold in slow motion compared to high-speed impacts, but it would be no less spectacular. The Sun's gravity would begin shredding the planet at about 30 solar radii from the surface, far outside the corona. But unlike a small comet that disintegrates quickly, a planet-sized object would take months to be completely torn apart and consumed. The process would create a temporary ring system around our Sun, like a cosmic Saturn, with rings made of molten rock and vaporized metal instead of ice particles. This debris disk would spiral inward over a period of months, with material constantly raining down onto the Sun's surface and releasing enormous amounts of energy. The total energy release would be staggering, roughly 10 to the 35th joules, enough to temporarily increase the Sun's brightness by a full %. From Earth, we'd witness something unprecedented in human history. Our supposedly stable, predictable star would suddenly become noticeably brighter. Growing seasons would extend, global temperatures would rise, and astronomers worldwide would scramble to understand why the Sun had suddenly hiccuped. But perhaps the most unsettling scenarios involve objects composed of materials we've never encountered before. Interstellar space is a laboratory for exotic physics, with conditions that don't exist anywhere in our solar system. Temperatures approach absolute zero. Densities can be millions of times lower than the best vacuum we can create on Earth. And magnetic field strengths can vary by orders of magnitude. Under these conditions, matter might organize itself in ways we haven't predicted. What if an interstellar visitor was composed primarily of metallic hydrogen, a state of matter that requires pressures found only in the cores of giant planets? Or what if it contained significant amounts of strange matter, hypothetical particles that might be stable under certain conditions, but would release enormous energy if disturbed? Even more exotic possibilities involve the remnants of stellar explosions. When massive stars go supernova, they can eject material at velocities approaching 10% the speed of light. Most of this material is ordinary atoms moving at extraordinary speeds, but supernovas also create conditions where the normal rules of nuclear physics break down. They forge elements that don't exist anywhere else in the universe, create isotopes with half-lives measured in minutes, and might even produce forms of matter that we haven't discovered yet. What if our next interstellar visitor was a chunk of neutron star material, somehow ejected during a stellar collision and now wandering the galaxy? Neutron star matter has a density so extreme that a teaspoon would weigh as much as Mount Everest. Even a tiny fragment, just a few centimeters across, would have enough mass to significantly perturb planetary orbits if it passed through our solar system. When such an object hit the Sun, the energy release wouldn't just be from kinetic impact. The neutron-rich material would trigger a cascade of nuclear reactions as it interacted with the normal matter in our star. The result might be a brief but spectacular increase in the Sun's energy output, creating a mini supernova event that would be visible from other star systems. And then there are the truly speculative possibilities that push the boundaries of known physics. Dark matter makes up about 85% of all matter in the universe, but we still don't know what it's made of or how it interacts with normal matter. Most dark matter particles seem to pass through ordinary atoms without any interaction at all. But what if there are rare forms of dark matter that can clump together and interact more strongly? Theoretical physicists have proposed the existence of dark matter nuggets, ultra-dense concentrations of exotic particles that might occasionally interact with normal matter in detectable ways. If such an object passed through our solar system, it might be almost entirely invisible until the moment it hit the Sun. Then, The interaction between dark matter and normal matter could release energy in ways we can't predict with current physics. Some models suggest that dark matter interactions might be able to trigger changes in the fundamental constants of physics in a localized region. If true, a dark matter impact on the Sun might temporarily alter the rate of nuclear fusion in our star's core, creating effects that would propagate outward over thousands of years. But let's bring this back to scenarios that are exotic, but still within the realm of known physics. The galaxy is full of stellar remnants, white dwarf stars, neutron stars, and black holes that occasionally get ejected from their birth locations by gravitational interactions. Most of these objects are far too massive to be significantly deflected by our Sun's gravity, but smaller fragments of disrupted systems might occasionally wander into our cosmic neighborhood. Imagine an object with the density of a white dwarf star, but only the size of a large asteroid. White dwarf material is so dense that a cubic centimeter weighs about as much as a car. A 1-kilometer chunk of this material would have a mass comparable to Earth's moon, all compressed into a volume small enough to fit inside a sports stadium. When this ultra-dense visitor encountered our Sun, the gravitational effects would be unlike anything in our solar system's history. The object would create massive tidal bulges in the Sun's surface as it approached, potentially triggering enormous solar flares and coronal mass ejections. As it finally impacted the solar surface, it would punch through the Sun's outer layers like a cosmic cannonball, creating a temporary crater kilometers deep before being absorbed into our star's interior. The energy released from such an impact would be visible across multiple star systems. Other civilizations, if they exist, might detect the sudden burst of X-rays and gamma rays from our Sun and wonder what catastrophic event had just occurred in our previously quiet solar system. These extreme scenarios raise profound questions about the long-term stability of our cosmic environment. For 4.5 billion years, our solar system has been a relatively quiet, stable place where life could evolve and flourish. But we're increasingly realizing that this stability might be more fragile than we thought. The galaxy is a dynamic, violent place where stars explode, black holes devour entire solar systems, and rogue objects wander through space at incredible velocities. Our solar system sits in what astronomers call the galactic habitable zone, a region far enough from the galactic center to avoid most catastrophic events, but close enough to benefit from the heavy elements created by stellar nucleosynthesis. But even in this relatively safe cosmic neighborhood, we're not immune to extreme events. Every 230 million years, our solar system completes one orbit around the galaxy, passing through regions of varying stellar density and encountering different populations of potential impactors. During passages through the galaxy's spiral arms, the rate of close encounters with other stars increases dramatically, potentially destabilizing the Oort cloud and sending showers of comets toward the inner solar system. Some scientists have proposed that these galactic passages might correlate with mass extinction events on Earth, creating a kind of cosmic clock that regulates the evolution of life on our planet. If true, then understanding the population of potential solar impactors isn't just an academic exercise. It's essential for predicting the long-term habitability of our world. The discovery of interstellar visitors like Oumuamua and Comet Borisov has forced us to expand our thinking about potential threats. We're no longer just monitoring objects that have been orbiting our Sun for billions of years. We now have to consider visitors from across the galaxy, each one potentially carrying exotic properties and extreme velocities that could create unprecedented effects if they encounter our star. This realization has sparked intense interest in developing early warning systems for interstellar objects. The Vera Rubin Observatory, coming online in the next few years, will be able to detect objects like Oumuamua while they're still years away from their closest approach to the Sun. Future space-based telescopes might be able to spot incoming visitors while they're still decades out, giving us time to study them, understand their properties, and potentially even launch interceptor missions to gather samples. But perhaps the most important lesson from these extreme scenarios is humility. The universe is vast, ancient, and full of phenomena that challenge our understanding of physics and astronomy. Every time we think we've catalogued all the possible ways that cosmic objects can interact with our sun, the universe surprises us with something new. The next interstellar visitor might be perfectly ordinary, another icy comet or rocky asteroid that follows predictable physics as it meets its doom in the solar furnace. But it might also be something so unusual, so extreme, that it forces us to rewrite our textbooks and reconsider our assumptions about how the universe works. Either way, we're watching. Our telescopes scan the sky continuously, our spacecraft monitor the space around our sun, and our computers simulate every conceivable scenario. We're the first generation of humans to seriously consider the possibility that our cosmic environment might not be as stable and predictable as we once thought. And that's both thrilling and sobering, because it means we're finally beginning to understand our true place in a universe that's far stranger and more dynamic than we ever imagined. Every clear night, as most of the world sleeps, a network of electronic eyes turns skyward in one of humanity's most important but least visible endeavors. These aren't casual stargazers or weekend astronomy enthusiasts, though those folks play a crucial role too, as we'll see. These are robotic sentinels, methodically scanning the heavens with the kind of relentless precision that only machines can maintain, hunting for cosmic dangers that could change life on Earth forever. The Catalina Sky Survey in Arizona is one of the most prolific of these cosmic watchdogs. Night after night, its telescopes sweep across predetermined patches of sky, taking thousands of images that are immediately fed into sophisticated computer systems. These machines analyze each image for the telltale streak of a moving object, something that appears in one spot in the first image, has moved slightly in the second image taken a few minutes later, and continues its predictable path across the starfield in subsequent images. And if the thought of alien visitors isn't enough to capture your imagination, consider this. Every single one of these encounters, whether it's a comet from our own Kuiper Belt or a mysterious interstellar wanderer, represents a collision between the known and unknown, a cosmic experiment in extreme physics that we're only just beginning to understand. When these objects approach our sun, they don't just vaporize quietly. They create spectacular light shows, generate shockwaves that ripple through the solar atmosphere, and sometimes trigger magnetic storms that can affect space weather all the way out to Earth's orbit. Every impact is like ringing a cosmic bell, sending waves and disturbances propagating through our entire solar system. The sun has been playing this cosmic game of pinball for 4.5 billion years, and we've only recently learned how to keep score. Every day brings new discoveries, new understanding of just how dynamic and interconnected our cosmic neighborhood really is. So as we embark on this journey together, exploring the incredible physics of what happens when space attacks the sun, remember that we're not just talking about abstract science. We're talking about a process that's been shaping our solar system since before Earth even existed, a cosmic dance that continues right now above our heads every single night. And the best part, we're living through the golden age of discovery, with new telescopes coming online, spacecraft flying closer to the sun than ever before, and detection systems that can spot visitors from other stars while they're still years away. We're about to learn things about our cosmic environment that would have seemed like pure fantasy just a generation ago. But first, we need to understand how we got here. How did our sun become such a popular target? What happened during those violent early days when our solar system was still taking shape? And why does it seem like every time we think we've figured out the rules of this cosmic shooting gallery, the universe throws us a curveball that changes everything? Let's find out together. So now that you know our sun sits in this cosmic shooting gallery, let me take you back to where this whole wild story really begins. We need to travel way, way back in time, 4.5 billion years ago to be exact. Picture this. Our sun isn't the stable, mature star we know today. It's a cosmic toddler barely formed, and let me tell you, it's making one heck of a mess. In the beginning, chaos absolutely reigned. Our infant sun was surrounded by what astronomers call a protoplanetary disk, basically 100 Earth masses worth of leftover building materials from stellar formation. We're talking about rock, ice, and dust, all swirling around in this incredible gravitational maelstrom. Imagine the most chaotic construction site you've ever seen, then multiply that by about 1 trillion and set it in space. That's what our early solar system looked like. Here's what's wild about young stars. They're incredibly messy eaters. And our sun was no exception to this rule. Picture a cosmic buffet where everything is flying around at thousands of kilometers per hour, and you've got this hungry young star in the middle, gravitationally grabbing everything it can reach. Every few minutes, and I mean every few minutes, another chunk the size of Mount Everest would spiral into the sun's gravity well and just vanish in a brilliant flash of vaporized rock and ice. Think about that for a second. Every few minutes, something the size of the world's tallest mountain would disappear in a burst of energy that would make our most powerful nuclear weapons look like firecrackers. The early solar system was like the ultimate cosmic demolition derby, with collisions so frequent and so energetic that the sun's surface literally couldn't cool down between impacts. The energy being released was absolutely staggering. Each impact delivered more energy than all of human civilization has used in our entire history, and this was happening continuously for millions of years. The sun was basically being carpet-bombed by mountain-sized projectiles, and the bombardment was so intense that our star was actually brighter and more active than it is today, despite being younger and smaller. But here's where it gets really interesting. This wasn't just random destruction, it was construction in disguise. All of this cosmic violence was actually the process of our solar system organizing itself. Jupiter was forming out there in the cold outer regions, growing massive enough to start bullying smaller objects around with its gravity. Saturn was doing the same thing. These giant planets were like cosmic vacuum cleaners, sweeping up material and fundamentally reshaping the architecture of our entire solar system. And then something remarkable happened. Jupiter started migrating inward. Computer simulations show that our giant planet actually moved much closer to the sun than it is today, then mysteriously migrated back outward. This cosmic shuffle had profound consequences for everything else in the solar system. As Jupiter moved around, its massive gravity field acted like a cosmic slingshot, flinging ice-rich comets from the outer solar system toward the inner planets. This is where the story gets personal for us here on Earth. Those Jupiter-flung comets weren't just cosmic debris, they were water delivery systems. During what scientists call the Late Heavy Bombardment, about 4 billion years ago, our young planet was getting pummeled by these icy visitors from the outer solar system. Each impact delivered not just energy, but precious water and organic compounds. In a very real sense, the cosmic chaos that was devastating the early solar system was also seeding Earth with the ingredients for life. Fast forward through the eons, past the formation of the planets, past the cooling of Earth's surface, past the emergence of life itself. Jump ahead to just 2,000 years ago, when Chinese astronomers were doing something absolutely remarkable without even realizing it. They were meticulously recording what they called broom stars, comets that swept close to the sun with their distinctive tails trailing behind them like cosmic broomsticks. These ancient astronomers had no idea they were documenting solar system archaeology in action. Every comet they recorded was a time capsule from the formation of our solar system, a dirty snowball that had been orbiting in the cold outer reaches for billions of years before finally taking a dive toward our star. They were watching the ongoing cleanup process, the final act of solar system formation playing out in slow motion across the centuries. Some of these ancient encounters were absolutely spectacular. The Great Comet of 1843 came so close to the Sun that observers could see it in broad daylight. Imagine looking up at the afternoon sky and seeing a comet so bright it outshone everything except the Sun itself. Its tail stretched halfway across the sky, a ghostly banner visible even through the glare of daylight. People were terrified, thinking it was an omen of the end times. They had no idea they were witnessing one of the most extreme close encounters between a comet and our star in recorded history. But the real revolution in understanding solar impacts came with the space age. Suddenly, we had eyes in space, telescopes and cameras that could watch the Sun continuously without worrying about clouds or daylight or atmospheric interference. And what we discovered completely transformed our understanding of how active and dynamic the space around our Sun really is. The Sungrazer project has made this kind of citizen science even more accessible. You can literally sit at your computer, download images from space-based solar observatories, and search for new comets diving toward the Sun. The project provides software that walks you through the process, teaching you how to distinguish between genuine comet discoveries and the various artifacts that can fool inexperienced observers. This democratization of discovery has been phenomenally successful. Amateur astronomers have discovered hundreds of sun-grazing comets through the Sungrazer project, contributing to our understanding of these cosmic death spirals from their living rooms and home offices. In 2023 alone, amateurs discovered over 400 comets, many of them in their final hours before vaporizing. In the solar corona, the collaboration between professional and amateur astronomers has created a global network of watchers that operates 24 hours a day, 7 days a week. When professional surveys detect something interesting, amateur astronomers around the world can be alerted within minutes to provide follow-up observations. When amateurs spot something unusual, the professional community can quickly mobilize major telescopes to confirm the discovery and determine its significance. This network proved its value during the discovery of Oumuamua. Within hours of Robert Varick's initial detection at the Pan-STARRS telescope, observatories around the world were tracking this mysterious visitor, gathering the data needed to understand its unprecedented properties. The global response was so rapid and coordinated that we managed to squeeze maximum science out of the brief time this interstellar messenger spent in our cosmic neighborhood. But the watching isn't limited to Earth-based telescopes. We have an entire fleet of spacecraft monitoring different aspects of our cosmic environment. The Parker Solar Probe flies through the solar corona, measuring the aftermath of comet impacts and mapping the complex magnetic field structures that channel solar wind throughout our solar system. The Solar and Heliospheric Observatory continues its decades-long vigil, discovering new sun-grazing comets almost daily. NASA's NEOWISE mission uses infrared light to spot asteroids that might be too dark to detect in visible light. Infrared observations can reveal objects that absorb sunlight rather than reflecting it, asteroids composed of materials that make them nearly invisible to traditional surveys. NEOWISE has discovered thousands of previously unknown near-Earth objects, including some that pass uncomfortably close to our planet's orbit. The European Space Agency's Gaia mission is creating the most precise map of our galaxy ever assembled, measuring the positions and motions of over 1 billion stars. While Gaia's primary mission focuses on stellar astronomy, its incredibly precise measurements can also detect the gravitational effects of passing objects, potentially spotting rogue planets or massive asteroids that might otherwise remain invisible until they enter our inner solar system. But perhaps the most important aspect of this cosmic surveillance network is its international character. Asteroids and comets don't respect national boundaries, And defending our planet requires cooperation between countries that might disagree about everything else. The detection and tracking of potentially hazardous objects has become one of the few areas where global scientific cooperation really works, with data freely shared between observatories regardless of political tensions. The International Astronomical Union coordinates the naming and cataloguing of new discoveries, ensuring that every detected object gets a unique identifier that scientists worldwide can use to share observations and coordinate research. The Minor Planet Center serves as a global clearinghouse for observations, automatically processing data from telescopes on every continent and making the results available to researchers everywhere. This cooperation has created a system that's remarkably resilient and comprehensive. If one observatory is clouded out, others can pick up the slack. If one country's space program encounters problems, other nations can provide backup capabilities. The network has multiple redundancies and overlapping coverage that makes it extremely unlikely that a dangerous object could slip through undetected. The detection capabilities continue to improve every year. New telescopes come online, existing facilities upgrade their cameras and computers, and the algorithms that process the data become more sophisticated. Machine learning systems that can spot asteroids in conditions that would fool human observers. Automated follow-up systems that can track newly discovered objects and predict their orbits with incredible precision. But the network isn't just about finding potentially dangerous objects, it's about understanding them. Every detection provides data about the composition, rotation, and orbital characteristics of these cosmic visitors. Spectroscopic observations can reveal what they're made of. Photometric measurements can determine how fast they're spinning and whether they're solid rocks or loose piles of rubble held together by weak gravity. This information is crucial for planetary defense because different types of asteroids require different deflection strategies. A solid metallic asteroid might be nudged off course by a kinetic impactor, essentially a cosmic billiard ball collision. But a loose rubble pile might just absorb the impact without changing course, requiring more subtle approaches like gradually heating one side with focused sunlight to create tiny but persistent thrust. The sea watching also extends to monitoring the effects of space, weather on our technological civilization. Solar flares and coronal mass ejections can disrupt satellite communications, damage power grids, and pose radiation hazards to astronauts. The same network that watches for asteroid impacts also tracks these invisible threats from our own star, and the network is constantly evolving. New technologies are being tested that could detect even smaller objects or provide longer warning times. Concepts for space-based telescopes that could spot incoming asteroids from directions impossible to observe from Earth. Artificial intelligence systems that could predict where to look for the most dangerous objects based on orbital dynamics and gravitational perturbations. The goal is to create a system so comprehensive and sensitive that nothing dangerous can approach our planet without being detected, characterized, and tracked. We want advance warning measured in years or decades, not days or hours. We want to know not just that something is coming, but exactly what it's made of, and how best to deflect it if necessary. The watchers are everywhere now, professional and amateur, human and artificial, terrestrial and space-based, all united in mapping the cosmic bullets whizzing through our celestial neighborhood. They're the early warning system for a civilization that's finally waking up to the realities of life in a dynamic, sometimes dangerous universe, and they're just getting started. Because the next generation of telescopes and spacecraft will reveal cosmic phenomena we haven't even imagined yet. As we reach the end of our journey through the cosmic shooting gallery that surrounds our sun, I want you to consider something profound. Every impact we've discussed tells a story written in light and atoms, a cosmic narrative that connects our solar system to the entire galaxy and reveals our place in a universe far more interconnected than most people realize. Every single collision, every spectacular vaporization, every moment when space attacks our sun is like opening a time capsule from somewhere else in the universe. These aren't just random acts of cosmic violence. They're information packages, carrying chemical signatures and physical properties that teach us about stellar evolution, planetary formation, and maybe even the distribution of life throughout our galaxy. Let me start with an example that revolutionized our understanding of what these cosmic impacts can reveal. In July 1994, humanity witnessed something unprecedented. Comet Shoemaker-Levy 9 slammed into Jupiter in a series of 21 spectacular impacts that created Earth-sized scars in the giant planet's atmosphere. For the first time in human history, we watched a cosmic collision unfold in real time. And what we learned changed everything. The impacts weren't just spectacular light shows. They were incredible natural experiments that dredged up material from deep within Jupiter's atmosphere, giving us our first direct look at chemistry that had been hidden beneath the clouds since the planet's formation. Spectroscopes around the world analyzed the light from these cosmic explosions, reading the chemical fingerprints in the wavelengths emitted by vaporized comet material and Jovian atmospheric gases. We detected water vapor, carbon monoxide, hydrogen sulfide, and dozens of other compounds that told us about both the comet's composition and Jupiter's internal structure. For the first time, we could see below Jupiter's cloud tops and sample the planet's deep atmosphere without sending a spacecraft plunging into its crushing depths. The same principle applies to every solar impact, but on an even more profound scale. Each object that meets its doom in our star's furnace undergoes complete atomic disassembly, breaking down into its constituent elements and revealing its chemical makeup through the specific wavelengths of light emitted during vaporization. It's like having a cosmic mass spectrometer that can analyze any object in our solar system, as long as we're willing to watch it be destroyed in the process. Rocky asteroids create distinctive spectral signatures that tell us about the conditions in the early solar nebula where they formed. Iron and nickel from metallic cores create different patterns than the silicate minerals found in stony asteroids. Icy comets reveal the isotopic ratios of water and organic compounds that were present in the outer solar system billions of years ago. But the really exciting discoveries come from interstellar visitors, because they carry chemical messages from alien solar systems. When astronomers detected water, carbon monoxide, and other familiar molecules in Comet Borisov, they weren't just confirming that this object came from another star. They were reading the chemical inventory of a completely different planetary system, ingredients that could potentially seed life under the right conditions. This raises one of the most profound implications of the cosmic impact process: the possibility that life itself might be a galactic phenomenon. Spreading from star to star through natural processes we're only beginning to understand. The concept is called lithopanspermia, and it suggests that microorganisms might be able to survive the incredibly harsh journey between star systems, hitching rides on asteroids and comets that get ejected from their home systems and eventually captured elsewhere. It sounds like science fiction, but laboratory experiments have shown that certain extremophile bacteria can survive conditions far more hostile than anything they'd encounter during interstellar travel. Think about what this means. Every impact might be delivering not just chemical building blocks for life, but actual living organisms from other worlds. The organic molecules that kick-started the evolution of life on Earth might originally have come from another star system, carried here by ancient interstellar visitors that arrived billions of years ago when our planet was still cooling. If lithopanspermia is real, then the galaxy might be teeming with related forms of life, all descended from common ancestors that spread from world to world through the slow but persistent process of interstellar exchange. We might not be alone in the universe. We might be part of a vast biological network that spans the entire galaxy, connected by cosmic travelers that carry genetic material between the stars. But even if life doesn't literally travel between stars, the chemical signatures carried by interstellar visitors are teaching us incredible things about the conditions around other suns. When we detect phosphorus, sulfur, and other bioessential elements in objects from alien solar systems, we're glimpsing the chemical inventory that might be available for life to evolve in those distant places. The connections run deeper than just biology, though. Our sun orbits the galaxy every 230 million years, and this cosmic journey takes us through regions of varying stellar density, different populations of potential impactors, and changing gravitational environments that affect everything from comet orbits to the rate of interstellar encounters. During passages through the galaxy's spiral arms, where star formation is most active, the rate of close encounters with other stellar systems increases dramatically. These cosmic seasons might correlate with major changes in Earth's geological and biological history, including mass extinction events that have repeatedly reshaped the evolution of life on our planet. Some scientists have proposed that these galactic passages create a kind of cosmic clock that regulates the long-term evolution of planetary systems. When our solar system passes through a spiral arm, gravitational perturbations from nearby stars might destabilize the Oort cloud, sending showers of comets toward the inner solar system and increasing the bombardment rate on all the planets. This could explain the apparent periodicity in mass extinctions that paleontologists have detected in Earth's fossil record. Every 26 to 30 million years, life on our planet seems to face a major crisis that eliminates large numbers of species and creates opportunities for evolutionary innovation. The timing roughly matches our solar system's oscillation above and below the galactic plane, suggesting a cosmic connection to biological evolution. The implications are staggering. If true, it means that the evolution of life on Earth has been shaped not just by terrestrial processes like climate change and volcanism, but by our solar system's journey through the galaxy itself. We're not just products of our planetary environment, we're products of our galactic environment, shaped by cosmic forces operating on scales we're only beginning to appreciate. But the cosmic connections don't stop with biology. Every major solar impact creates energy and particle disturbances that propagate throughout our entire solar system, potentially affecting planetary atmospheres, magnetic fields, and space weather patterns that can influence conditions on worlds millions of kilometers away. The energy released by massive impacts doesn't simply vanish into space. It propagates outward as enhanced solar wind, shock waves in the interplanetary magnetic field, and cascades of high-energy particles that can affect atmospheric chemistry on every planet in our solar system. The Parker Solar Probe has detected magnetic disturbances from solar impacts that continue to influence space weather conditions. Weeks or months after the original collision, this raises fascinating questions about the role of solar impacts in planetary evolution. Mars once had a thick atmosphere that protected its surface from radiation and might have supported liquid water for billions of years. But the solar wind gradually stripped away this protective envelope, leaving Mars the cold, dry world we see today. Did ancient solar impacts accelerate this atmospheric loss by creating periods of enhanced solar wind activity? Could massive comet impacts have triggered the coronal mass ejections that blasted away Mars's atmosphere? The planet's proximity to the asteroid belt would have exposed it to more frequent impacts than Earth experiences, and each collision might have contributed to the gradual erosion of the Martian environment. Understanding these cosmic connections isn't just academic curiosity, it's survival. Intelligence for a civilization that's beginning to spread beyond its home world. As we establish permanent settlements on Mars, the Moon, and eventually other planets, We need to understand how solar impacts and space weather affect atmospheric retention, radiation exposure, and the long-term habitability of these environments. The same processes that shaped Mars's evolution will affect any terraforming efforts we undertake on other worlds. If we're going to give Mars a new atmosphere, we need to understand how to protect it from the solar wind and cosmic radiation that stripped away the original one. If we're going to establish permanent colonies throughout the solar system, we need to predict and prepare for the space weather events triggered by major solar impacts. But perhaps the most profound realization is that studying solar impacts has revealed our solar system to be part of a vast galactic ecosystem, constantly exchanging material with other star systems through processes that have been going on since the galaxy was young. We're not isolated observers of the cosmic drama. We're active participants in a story that spans billions of years and countless worlds. Every interstellar visitor that reaches our sun carries information about the conditions around its parent star, the chemistry of its birth environment, and potentially even biological signatures from alien worlds. Every impact is a cosmic message, written in the language of physics and chemistry, telling us about the diversity of planetary systems throughout our local region of the galaxy. As our detection capabilities improve and new telescopes come online, we're going to receive more of these messages than ever before. The Vera Rubin Observatory will spot interstellar visitors while they're still years away from the Sun, giving us time to study them in detail and perhaps even send spacecraft to intercept them for direct analysis. Future space missions might be able to collect samples from these cosmic messengers before they're destroyed in the solar furnace, bringing alien materials back to Earth for detailed laboratory analysis. We might finally be able to answer questions about the chemical and biological diversity of our galactic neighborhood without having to travel to other star systems. But the cosmic connections extend beyond just receiving visitors from other stars. Our solar system is also sending its own ambassadors into the galaxy, as Jupiter's gravity occasionally flings comets and asteroids onto trajectories that will carry them to other star systems. In a few million years, some civilization around another star might detect objects from our solar system and wonder about the conditions around our sun. This galactic exchange has been going on for billions of years, creating a vast network of cosmic communication that operates on timescales far longer than human civilization. We're just now learning to read these messages and understand our place in this galactic community. The study of solar impacts has also revealed that our sun itself is an active participant in shaping the cosmic environment around us. Every impact changes the solar wind, affects the magnetic field structure throughout our solar system, and creates disturbances that propagate outward to influence conditions on distant planets and moons. This means that the sun isn't just a passive target for cosmic bombardment. It's a dynamic system that responds to every impact and broadcasts those responses throughout our entire cosmic neighborhood. Changes in solar activity triggered by major impacts might affect atmospheric chemistry on Earth, influence the formation of clouds and weather patterns, and even modulate the cosmic ray flux that reaches our planet's surface. Understanding these connections is becoming increasingly important as we develop more sophisticated climate models and try to predict how Earth's environment will change in the coming centuries. Solar variability has always been a factor in terrestrial climate, but we're now realizing that this variability might be influenced by the cosmic bombardment rate and the types of objects encountering our stars. We stand on the threshold of becoming a truly interplanetary species, with permanent settlements spreading throughout our solar system. Understanding these cosmic connections isn't just scientifically fascinating, it's essential for our long-term survival and prosperity. We need to know how solar impacts affect space weather, how interstellar visitors might influence our technological infrastructure, and how the galactic environment shapes the evolution of planetary systems. The age of interstellar archaeology has begun, and we're the first generation of humans to participate in it. Every new impact teaches us something about our galaxy. Every interstellar visitor carries messages from alien worlds, and every discovery brings us closer to understanding our true place in the cosmic community. We've learned that our sun sits at the intersection of countless cosmic highways, with traffic flowing in from every direction, carrying information about the formation and evolution of planetary systems throughout our local region of the galaxy. We've discovered that space isn't empty, but filled with wandering objects that connect star systems through processes operating on billion-year timescales. Most importantly, we've realized that we're not isolated observers of the cosmic drama, but active participants in a galactic ecosystem that has been exchanging material, energy, and potentially even life itself since the universe was young. Every impact, every visitor, every cosmic collision is part of a story that connects us to the stars themselves. The sun will continue to be bombarded by visitors from across the galaxy for billions of years to come, and we'll be here to watch, learn, and gradually piece together the cosmic connections that make us not just citizens of Earth, but citizens of the galaxy itself. And that's a story that's still being written, one impact at a time, in letters of light and atoms against the backdrop of our magnificent, dangerous, absolutely fascinating cosmic neighborhood.